All right. Student uses a spring scale, remember that measures force, it's like your force probe, to exert a horizontal force on a block, pulling the block over a smooth floor. I assume that means no friction. The student repeats the procedure several times, each time pulling the block from rest through a distance of 1 meter. For which of the following graphs of force as a function of distance will the block be moving the fastest at the end of 1 meter? Okay. All right. So, if you watch the previous question, we talked about force versus distance graph, that the area under a curve is the work done. There is a connection here, though, between the work done and moving the and the speed. Do you remember what it is? So, by the way, if he pulls on a smooth floor, the only force on it is the force he's pulling with. The only force that matters. There's weight and normal force, they cancel. That means he's pulling with a net force. You know the net. This is actually the net force in that case. So what do you know? Net work is equal to a change in kinetic energy. So whichever one has a bigger net work, all right, work done, it's going to have a bigger change in kinetic energy. But they all start at rest. So whichever has the biggest change in kinetic energy, the only way to have that bigger change is to be moving faster, as long as it's the same object. So whichever one, this is a fancy way of saying find the area under the curve again. So this area would be right here, and that's going to be 1 times 3, so it's 3 joules. This one is, let's see, this is 1.5, and this area here is half a unit from here. Oops, sorry. Make sure you can see it. Hold on. There we go. So this is 1.5 right in here. This here is half times 6, that's 3. So the total area under the curve here is, I'll write it over here, is 4.5 joules. This one was 3 joules. So far, B is the winner. Let's go on, look at the others. Ooh, we got triangles and stuff to deal with. You're going to be all right. So area under here, 1 times 6 is 6, but then cut it in half because it's a triangle, 1/2 base times height, so it's going to be 3 joules. Then this area, let's see, that's let's just do this right here. Here, break it up that, and we'll see if this orange shows up. There we go. We'll break it up, this piece separately from it. So this yellow piece right here has an area of 3. This area here is half times 3, but cut it in half. So it's half of 1.5, so it's 0.75. Another way to do this, by the way, would be to just say, all right, how much is each block? And that would be a half times 3, which is 1.5. So 1.5, 1.5, and then half of 1.5. So that works. So this would be 3.75 joules. And the winner is B then, with the largest area. Probably could have done that just by visually inspecting it, but it's not worth it. I mean, it's worth doing the calculations. This is 17, just making sure, yep, B is the correct answer. Okay, 18. So 18 gets split on pages, so we're just going to try to fit it all in here. Okay, 18 looks like this. We'll look at the graph and the description first. So they have a velocity versus time graph. That's a little bit, we haven't seen that in a while. The graph above shows velocity versus as a function of time for a 0.5 kilogram object, so they give us the mass, traveling along a straight line. The graph has 3 segments labeled 1, 2, and 3. A rope exerts a constant force of magnitude F1 on the object along its direction of motion the whole time. So wait a second. But there's definitely a change in velocity here. So the net force can't be constant, but they're saying that the force, the tension in the rope, is always the same. During segment 2 only, a frictional force of magnitude whatever is exerted on the object. So here it speeds up at a certain rate based on the acceleration, which is based on the net force, which is just the tension. Then all of a sudden it hits friction, and the net force is a combination of the friction and the tension, and it must actually, the friction must be more because it slows it down. Right? It's not like it speeds up less quickly, it slows down. So I'm thinking this is telling me that the force of friction is going to be more, magnitude-wise, more than the force of that tension. We'll come back to that. Then, notice it starts, when some friction's gone, it picks up speed in the exact same slope, the exact same manner. Alright, so let's see what they want us to find. That's just going with what I know when I look at the interpreting the diagram. Now we'll see if any of that helps me with the problem. For another identical object at rest, no friction force is exerted during segment 2. A rope exerts the same constant force of magnitude as the previous scenario. What is the change in the object's kinetic energy during segment 2 for another identical object at rest? Like, they couldn't make this any more complicated, and it's not not in a good way. All right, so they do the same thing with the same object. They want to know the change in the object's kinetic energy from 2 to 4 seconds. Okay. All right, so this would be the same. For our new object, this would be the same. But it would continue to do that. That's the trick here. It would not drop down. Is there another question to this? No. Seems like an awfully strange thing to do, but okay, we're just going to go with it. This part maybe doesn't even look like it matters. So we're going to say, what's my change in velocity here? Because that's important. Change in velocity over time. So the slope of a velocity versus time graph is your acceleration. I want to find the acceleration because net force is equal to ma. And if I'm going to figure out that force, I need to know, and times the distance. I can't just go straight to work. So we're gonna have to figure this out. So let's figure out the size of that force. That tension force, let's see, acceleration is going to be 4 meters per second increase in velocity in 2 seconds. So that means the acceleration is 2 meters per second squared. So I know the acceleration. I know the mass. They give me the mass is 0.5 kilograms. Okay. So I know that the size of that force, actually, do I need, I don't need that right away. Here's what I need. How fast is the thing going here? It's going 4 meters per second, right? Keep that in mind. So initially, let's go right here. So in fact here, ready? No. We're going to look at this graph. We're going to recreate it real quick. 1, 2, 3, 4, and over 1, 2. So it's here. It went from here to here on my graph. Now it's going to continue doing that. So up 2 over 1, up 2 over 1, up 2 over 1. How many seconds do I need to go for? I need to go for 2 more seconds. So really, this in pink is what we're worried about. Is that same from 2 seconds to 4 seconds. If there was no friction, what would the change in kinetic energy be? Well, easiest way that I can think of to do this, so this was 4, this is 5, 6, 7, 8, is to find the initial kinetic energy and the final kinetic energy using this graph. So we don't even need, if we just, now that we kind of continue that on, we don't actually even need to calculate the slope. If I know that the initial kinetic energy is 1/2 0.5, the mass of the object, times the initial velocity squared, so 4 meters per second squared. And the final kinetic energy is 1/2 the same mass of the object times its final kinetic energy, 8 meters per second squared. And I find out what each of those are and subtract them, I should have my answer. So in the case of the bottom, that's 16 times a quarter, right? Half of a half is a quarter. That's 16. So a quarter of 16 is 4 joules. This is a quarter of 64, which, you know, I should be able to do in my head, but you know, it's 16. So this is 16 joules. So what's the change in kinetic energy? Well, it's going to be 12 joules, right? The final minus the initial, it went up 12 joules. Let's see if we have an answer that says 12 joules. We do. Now let's see if it's the right answer. 18. It is. There we go. So we did not actually need to calculate this. We just needed to say, all right, you could just realize it's going to, without friction, it's just going to continue doing what it was doing. And from the graph, we could pick the final and initial speeds, and with the mass, we can calculate the change in kinetic. $19. Ball is dropped and bounces off the floor. Its speed is the same immediately before and immediately after the collision. Well, okay, first of all, that's an impossibility, but that's okay. It's okay. Well, it dropped from a certain height. It has potential energy, right? That energy is turned all into kinetic just before it bounces. And that kinetic energy is the speed, right? It's locked into the speed. So it has a certain kinetic energy, it has a certain speed. If it comes off the floor with the same speed, remember, energy doesn't care about direction. If the V's are the same, then the KE here is the same as it is here, coming in and leaving. Normally this does not happen with the ball. Some of that energy is lost in friction, in the deformation of the ball. So, but in this case, they're telling us the speed here and the speed here are the same. The kinetic energies are the same. Well, that means that kinetic energy's got to go somewhere. It's going to rise up. It's going to turn into potential. If this energy, if these energies are the same, then the energies up here have to be the same. If there's no friction, it's got to be where it goes. So it should return to the exact same height. $20. Has a pendulum bob. Not all pendulums are named Bob, by the way. Some are named Tom. No, just kidding. Look what it's called, that Bob thing. Yeah, anyway, sorry. The pendulum illustrated above has a length of 2 meters. The bob has a mass of 0.04. Okay. They give us a cosine of the angle. So if the pendulum is released from rest, what is the maximum speed of the bob? Okay. So here's how we're going to look at this problem. Let's zoom in on this a little bit and see if we can make sense of it. So, what happens, what we need to know is this distance that it falls. Because that change in potential energy gets turned into kinetic. It doesn't matter how it happens. If there's no friction, it could be sliding down a ramp or just dropped. but this is the change in height. All right, from the center of this ball to the center of this one. So this little distance right here is what we need. Cool? Now I don't think I'm going to go draw this exaggeratedly on graph paper so that we can kind of make sense of how we're going to find that. So, pendulum, here's a dotted part of it. Boom, 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 boom. In fact, let's do this. All right, I'm gonna go a little farther. There we go. And I'm gonna, to exaggerate, I'm gonna start the pendulum bob way up here, but I gotta make sure they're the same length. So hold on, take one of these and say that long is the same as this long. All right, so the center of the ball is here and the center of the ball is here. There we go. Got that? Okay. This means that I've exaggerated, by bringing it up higher, I've exaggerated the size of this piece so we can reference it. All right, this is theta. This is 2 meters. Ultimately, I want this, the change in height is what I want. This is also 2 meters, right? It's the same pendulum piece. To get this, I really need to go after this. This is what the pink thing is, what I got to find first. And then, if I find that, I can subtract it from 2 meters, and that gives me my change in height. So let's figure out what this is. Well, for this angle, that is the adjacent, and we have the hypotenuse. So it's no doubt, it's no surprise that they gave us the cosine of that, because the cosine is what we need. So the cosine of this angle, right down here, is equal to the adjacent. What do we want to call that? I'm just going to call it pink. P for pink. Is the pink section divided by the hypotenuse, 2 meters. But they tell me the cosine is 0.9, flat out. So the cosine of our angle is 0.9. If I multiply both sides by 2, that's the length of the pink section there. Try to move that so you can see it. There we go. So it's 1.8. So this distance right here is 1.8 meters. So how long or how far is our drop? You can do this. If it's 2 meters, it's going to be, so delta y is 0.2 meters, this drop in height. There we go. Now I have enough to figure out the change in potential energy. I had this much and it went to 0. But that change in potential energy is now all in the form of what down here? You're right, kinetic energy. So let's figure out what change in potential energy that is first. We can do that here, I think. So we know that it drops delta y, so we know it's that its initial, we'll do it this way, its initial mechanical energy here, sorry, back that up. Initial mechanical energy here is equal to its final mechanical energy down here. But initially, it's all in the form of potential. So mg delta y, this change in height here, equals 1/2 mv at the bottom squared. First thing we notice here, by the way, is they didn't actually need to give us the mass. It'll divide out. It oftentimes does in these situations. In fact, always does. So we did find delta y. That was 0.2. So I have 10 for g times 0.2 equals half of this speed at the bottom squared. All right, so 0.2 times 10, that's 2. Double it, that's 4. So 4 equals v bottom squared. Take the square root, comes out evenly. The velocity at the bottom should be about 2 meters per second. Let's see. That is answer C, and the question is answer C correct? question is, where did I put my little thing with the answers on it? There it is. And let's see, this is 20. C. Okay, good. I'm not getting them wrong. I just hate when I get them wrong. As I'm sure you do as well. Okay, we are moving on to 21. We're getting close. I'm going to run out of time soon anyway, so it's good. When I'm doing this, I got my freshman class coming up. I'm going to Zoom with my freshmen. Me staring at a bunch of names on a screen. It's exciting. It really is. It's what I got into teaching for. All right, 21. Some students want to calculate the work done by friction as an object of unknown mass moves along a straight line on a rough surface. Students have a force probe, meter stick, and a stopwatch. Which of the following will allow the students to take the measurements needed? So I'm going to jump right into how to do this one, because this is actually a classic lab that, had we had some time, I might have actually done with you. But so here's how this works. You have a force probe, a meter stick, and a stopwatch. First of all, we're not going to need the stopwatch. We can measure our force, but what I don't know, it's on a rough surface, so there's friction, right? So since there's friction, I don't know what that force of friction is right now. But if you do it right, you will know. Here's what you do. You pull this thing, so it has its normal force, fine, and its weight, no big deal. You're going to pull this thing as close as you can at constant velocity. You're going to try to pull it so that it moves constant velocity. Doesn't matter how fast. It could be that. It could be this. All right? As long as it's constant. Or it could be this. As long as it's constant. But you're going to pull it at constant velocity. What does that mean about your pull and friction? Well, remember, that's a form of equilibrium. So your pull, the force applied, and friction have to be the same. So as you pull it at constant velocity, whatever force you're reading on your force probe is friction. So the trick here is to pull it at constant velocity, as close to it as you can get. Right. So that will give you your force of friction. If you measure the distance over which you do that, what do they want to know? The work done by friction? Yeah, so then all you got to do is measure the distance with the meter stick that you do that over, and you get the work done. So let's take a look. But that's the trick. If you pull with something larger than friction, the thing will accelerate, and you don't know what friction is, so you can't tell how much work it would do. So I would say unknown constant speed. It's fine if you don't know the speed, it just needs to be constant. And then do we want to, so we're going to use one of these two, and the question is do we want to measure the time or the distance? Well, work is force times distance, so it's that. In fact, if I was doing this when they're asking about work, I might be able to boil it down to C and D, because it's got to be distance. It's work, force times, it's got to be. So then it comes down to acceleration not, and the trick here that I wanted to point out to you is you're going to want to pull it at constant speed, because that way you'll know the actual force of friction, because it'll be the same as yours. All right, 22. We have to be quick on this one. I may have to do an addendum to this. I guess I could pause it, but that'd be a long time to pause it. All right, 22. I'm going to try to be quick. Running athlete, blah, 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 blah. We saw a question like this earlier. The mass doesn't matter. It all comes down to the speed. So they have the same speed. The masses are going to divide out. He's going to swing to a maximum of 1.8. The other guy's going to swing to a maximum of 1.8. Because the mgh at the start, sorry, the 1/2 mv squared at the start, the v is the same, mass is different, but it's going to divide out because it's equal to the potential energy at the end. So, yes. So this is just going to be 1.8. 23. Graph above shows the force exerted by a spring is a function of the length of the spring. A block on a frictionless table is pushed against the spring that is fastened to the wall. The spring is compressed until its length is 20 centimeters. You gotta be careful, that's its length, but we don't know how far it's compressed. The block is then released. Which of the following values closest to the kinetic energy with which a block leaves the spring? So this is energy in a spring is 1/2 the spring constant times the distance compressed. So that is not 20 centimeters in this case. This right here, the length of the spring when there's no force, that is the equilibrium position. So when it's not compressed, it's 3.3 meters long. They compressed it to a length of 0.2. So they compressed it 0.1 meters. That's how far it was compressed. I don't want the length of 0.2. I want how far it was compressed. So this is 0.1 meters K. Now, we need K, but we can find K. K is just going to be the slope of this line. It's the force per meter. So whatever the slope of this line is what we want. So this is going to be 0.1 change, and it's going to be 60 newtons. Interesting. So 60, change in y is 60 over change in x, which is 0.1. So that is going to be 600. Well, just one of those things where, yeah, 600. So our K value is 600 newtons per meter. So I know my distance compressed is that. This is 600 newtons per meter. This is 1/2, of course. So there. So whatever that spring energy is, it's a smooth surface. So the kinetic energy with which it leaves the spring is going to be the same. All of that will be turned into the KE after you let it go. So I got 0.1 squared times 300, basically. Boom. I get 3 joules. A. 23. A. Good. All right. 24. Moving quickly. I got my freshmen in, well, now. All right, so let me start setting them up.